Have you ever actually stopped to wonder how pressing a single physical key on your keyboard instantly translates into incredibly complex actions on your screen? Honestly, it feels like magic sometimes, right? But it's not magic. It's a highly orchestrated physical process executed with absolute perfect form. Today, we're going to look at the computer not just as a static box of wires and metal, but almost like a living, breathing organism. An organism equipped with a brain, senses, and memory.
Welcome to the Explainer. I am so excited to take you on this journey, deep inside the machine today. We're going to treat computer architecture exactly like human anatomy. It's all about perfect form and flawless execution. By the end of this session, I promise you're going to see your desktop, your laptop, and even that smartphone sitting next to you in a completely new light. Okay, let's dive right in. Here is our roadmap for today's Explainer. First up, the anatomy of a computer. Second, we'll go inside the brain, which is the CPU. Third, we map out the processing cycle. Fourth, we look at interacting with the world. And finally, number 5, memory versus storage. Section 1, anatomy of a computer. Let's start with the absolute foundation. Because whether you are using a massive high-powered desktop tower or just swiping on the smartphone in your pocket, the fundamental architecture operating beneath the glass and plastic is exactly the same. Notice the sheer universality of this model. Absolutely all computing devices operate on this very straightforward 4-step premise. First, you input qualitative information. Then, the machine instantly converts that human information into quantitative, numerical data. It then processes that data right in the center, sometimes storing it or recalling it from memory. And finally, it produces an output. Input, process, storage, output. That is the fundamental heartbeat of every single digital device on Earth. Before we continue, subscribe to our YouTube channel, Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Section 2, inside the brain, the CPU. Now, if that basic 4-step architecture is the body of our digital organism, this next part is the brain, the absolute central manager of the entire system. But to truly understand this modern brain, we actually have to travel all the way back in time to the 1940s. A mathematician and brilliant scientist named John von Neumann established a set of design principles back then that we still use today. I want you to really think about that for a second. The microscopic processors in today's bleeding-edge, hyper-fast devices are still fundamentally dictated by rules drawn up in the 1940s. It's incredible. The core rule of the von Neumann architecture? To work effectively, computer systems absolutely must store their programs in memory while they are actively running them. When you look at the central processing unit right there in the middle of this architecture, von Neumann noted that the microprocessor contains a few distinct crucial parts. You have the control unit. You can think of that as the strict manager directing all the electrical traffic and ensuring every instruction is followed with perfect form. Then you have the arithmetic logic unit, or ALU. As the name suggests, this is the heavy-duty calculator. It handles all the mathematical and logical operations, which makes sense since all data, at its core, is just numbers. And finally, sitting right alongside them, you have the registers. Now, those registers are fascinating. Think of them as the brain's extremely fast, extremely limited short-term memory slots. Data absolutely must be stored in one of these 5 specific registers before it can be processed. First up, for tracking the flow of instructions, you have the program counter. Its only job is keeping track of exactly where the next instruction lives. Meanwhile, the current instruction register holds the exact command that is happening right this very second. Next, for memory access, the memory address register remembers the precise location of the data the CPU needs to find, while the memory data register physically holds that actual data as it travels in and out. And finally, for all the heavy math, the accumulator acts as a sort of holding pen for the mathematical results the ALU just figured out. So, you might be wondering, what makes one digital brain vastly superior to another? Well, it comes down to these 3 massive performance multipliers. First, CPU cores. Instead of having just one control unit and one ALU, a dual-core or quad-core processor has multiple sets of them. This allows the brain to process multiple instructions simultaneously. Second is cache memory. This is a tiny, super-fast chunk of RAM built right into the chip itself, specifically for the data it uses most frequently. And third is clock speed, which we measure in gigahertz. When you see 1 gigahertz, that means the CPU is pulsing out 1 billion electrical cycles every single second, literally billions of operations in the blink of an eye. Section 3, the processing cycle. Okay, so we know the physical structure of the brain now. We've seen the hardware. But how does it actually think through all this massive amount of data? How does it read and execute our instructions so flawlessly? Let's see how all those components build into the famous fetch, decode, execute cycle. This entire cycle happens in tiny fractions of a millisecond. First, the CPU fetches the instruction from the RAM using those specific registers we just talked about to find the exact address. Then, it pulls that instruction into the current instruction register and decodes it, essentially translating it so the machine understands what to do. Finally, the arithmetic logic unit executes the command and stores the result. Fetch, decode, execute, over and over, billions of times a second with absolutely perfect execution. Stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCESE and turn on all notifications so you never miss our weekly exam strategy sessions. Now, the language the CPU uses during this fetch, decode, execute cycle is incredibly basic. It's made up of instruction sets containing opcodes and operands. The opcode is simply the action, the specific job it needs to do, like add or divide. The operand, on the other hand, is the target. It's the specific piece of data or the memory address that the action is applied to. Think about it like the digital equivalent of a verb and a noun. The opcode is the verb, and the operand is the noun. Section 4. Interacting with the world. We've spent a lot of time buried deep inside the processor, but here's the thing. A brain is completely useless without senses to perceive the outside world and limbs to interact with it. This brings us directly to input devices. You can think of these as the machine's sense of touch. On one hand, you have the classic keyboard, which is highly designed for complex, qualitative text entry. Every key sends a specific binary code. On the other hand, you have pointing devices like mice, trackballs, and touchpads. These are entirely different beasts. They physically translate your hand movements on a flat 2D surface into spatial, directional data on the screen. But what happens when the screen itself becomes the input device? Touchscreens are honestly incredible pieces of engineering. Resistive screens use actual downward physical pressure to push 2 layers together and change the voltage. Infrared screens emit an invisible grid of light across the glass and calculate exactly where your finger breaks the beam. But capacitive screens, like the sleek one on your smartphone right now, are entirely different. They literally rely on the human body being naturally conductive. Because we are full of water and salt, we conduct electricity. Capacitive screens use the tiny electrical currents flowing naturally through your fingertip to calculate exactly where you touched. No pressure needed, just your own electricity. Beyond just human touch, computers often need to sense the environment completely autonomously. This is where sensors come in, acting as highly specialized environmental organs. For instance, a computer can use a pH sensor to constantly monitor acidity levels in a massive water treatment plant. Or it can use an infrared sensor to measure precise distance and speed at a professional sporting event. Or consider a proximity sensor, detecting the physical presence of objects in a high-tech security system without any physical contact at all. Once the computer's brain takes in and processes all that sensory data, it very often needs to react in the physical world. To do this, it uses an output device called an actuator. An actuator is essentially a mechanical muscle. When the CPU sends the electrical command, the actuator physically moves. A perfect everyday example of this is the tiny, precise motor hidden inside a digital camera lens. When you give the digital input to zoom, the actuator mechanically extends or retracts the physical lens. Section 5. Memory versus storage. Okay, to fully grasp computer architecture from top to bottom, we have to untangle one of the absolute most common points of confusion: the distinct difference between how a machine remembers things in the short term versus how it remembers them in the long term. But before we start talking about massive hard drives, we definitely should acknowledge that not all computers actually need huge amounts of storage. Think about an embedded system, like the computer hiding inside your modern dishwasher, or a dedicated GPS unit. Because these embedded devices have highly specific, totally dedicated functions, and you certainly aren't saving family photos or installing heavy software updates on your dishwasher, their memory and storage requirements are incredibly small compared to a general-purpose laptop. For our general-purpose machines, though, like your laptop or phone, we have a very strict division. Primary storage, which includes RAM and ROM, is the computer's active memory. It is volatile, meaning the literal moment you cut the electrical power, the RAM totally forgets everything it was holding. It drops it all. It's essential just for the computer to power up and function in the moment. Secondary storage, however, like your hard disk drive or your solid-state drive, is non-volatile.
That is where all your actual files, your applications, and your music live safely, permanently, even when the battery dies and the screen goes black. Let's look closely at the incredible physical mechanics of that secondary storage. Inside an open magnetic hard disk drive, you have these perfectly engineered metal platters coated in a magnetic material, and they are spinning at absolutely incredible speeds. Hovering just microscopic fractions of a single millimeter above them is an electromagnetic read/write head. It literally floats on the cushion of air generated by the spinning disks, instantly altering the magnetic state of the platter to save your data permanently. It's a mechanical gymnast sticking a flawless landing millions of times over. Which leads us to a fascinating final thought to leave you with today. We all treat our digital lives as if they are permanent, tangible things. But if the machine's primary memory, its active thinking brain, wipes completely clean the very second the power drops, where does your digital life truly exist? It exists entirely frozen in microscopic magnetic fields on a metal plate, or trapped invisibly in the wiring of flash memory cells, just waiting for the CPU to wake up, fetch it, and bring it back to life. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.